So we're going to start working on projectiles at an angle. Projectiles at an angle follow the exact same rules as those for horizontally launched projectiles. And so all we're doing is adding just a little bit, but you've even done that little bit before. So all we have to do is put it together and you should be good to go. So let's get started. Objects launched at an angle have an initial velocity you have to break into x and y components. Then we're going to add those components to their corresponding side, the x side or the y side of our x and y motion chart. And I'll show you how to do that in a little bit. The thing you have to notice is that unlike the horizontally launched projectiles where we were on like a cliff or something like that, or a bird or something, where we just had one side and it went down, the projectile went down, we are working more like we did with the Kobe Bryant pull of snakes, and we have the whole thing. So at the highest point, we can say that we go up and it comes back down. So what goes up must come down. So we can use that to our advantage and make these problems a little bit simpler. And one other thing is that an object will travel the furthest in the x direction. So we have the y and we have the x. How do we do that? So we have the y and the x. It'll travel the furthest in the x direction when the angle is at 45 degrees. Okay? So, for example, this first one, an outfielder throws a baseball to the first baseman at a speed of 19.6 meters per second and an angle of 30 degrees above the horizontal. What is the initial horizontal and vertical velocities of the baseball? So first let's draw a picture. We have our outfielder. He has a ball in his hand and he's throwing it over here to another player. And he throws it over here. Okay? So approximately the distance in the y direction is the same because we're trying to make it so that their heights are the same. So this distance in the y and this distance in the y are the same. That'll come into play in a little bit. Not yet though. But we want to see what so this right here is what we are calling the initial velocity. And we said that it is 19.6 meters per second. And we've done this before. We need to break it into horizontal and vertical velocities. So we can make it we can turn it into a triangle. This right here is our 19.6. And that's our initial velocity. As we've done before, we are going to have, actually, since I have a better setup now, I can actually change colors a little bit better. Let's see. So, that's not what I wanted. Anyway, we'll just make the x blue and the y red. So this is VIY and this is VIX. Alright? So to find VIY, we want to say that, so this right here is our angle and it is 30 degrees. So we're going to be doing our friend SOHCAHTOA. So we have the triangle and we're looking for VIY. So we need something that's opposite over the hypotenuse. So opposite over hypotenuse is the sine of 30, or theta. And we're just going to plug things in and change it so that we aren't working with opposite over hypotenuse, but what we're actually dealing with. So right now it's sine of 30 is equal to the opposite, which is VIY, over a hypotenuse, which is 19.6. So then we have 19.6 sine 30. And that's going to get us 9.8 meters per second. Just generally, this 19.6 we can call VI, sine of our theta, whatever angle they give us. And then we can use that equation over and over again. This is in your reference table, actually. And this is equal to the velocity, the initial velocity in the y direction. Okay? So let's add a page so that we can talk about the x direction. Again, we have this. This is our 30. This is VI in the x direction. This is VIY, which we found to be 9.8 meters per second. And this is 19.6 meters per second. The VIX is similar to the VIY. It's going to be VIX over 19.6, whatever that is. And that is the adjacent over the hypotenuse. So we're looking at cosine here. So this is cosine theta. And we have our theta of 30. So it's cosine, well actually we can do cosine theta equals VIX over 19.6. That should be a decimal place right there. But I can't add it in. Anyway, it should be, so then we do times 19.6. And that makes it so these go away. And we can just erase them since I have that availability. So that's VIX. And more generally, that becomes VI cosine theta is equal to VIX. Alright? And this theta right here is 30, so we can replace it. And we get 16.97 meters per second. So this is 16.97 meters per second. So now we found the x and y components for this right here, and we should add our arrows so that we are, so that since it's a vector, they're all vectors. All right. So then the next thing is for you to try. It says a cannon elevated at an angle of 35 degrees to the horizontal fires a cannonball. If the ball lands 700 meters from the cannon 10 seconds after it was fired, what is the horizontal component of its initial velocity? So you can pause the video now and take a few minutes and try it out, and I will give you the answer in just a minute. So let's draw a picture. It says the cannon like that, something like that. This right here is the 35 degrees. So it's looking for, it says if the ball lands 700 meters from the cannon, so over here, this is 700, meters, and the time it takes for it to go that 700 meters is 10 seconds. So in the x direction, we have Vx equals d over t, just like you did with the horizontally launched projectiles. We still don't have any force in the x direction to speed it up or change it in any way, so we still use this equation. So it's just going to be Vx equals 700 meters divided by 10 seconds. So you get 70 meters per second in the x direction. So that's Vx, all right? If we want to find the velocity in the y direction, that's when we need to use SOHCAHTOA. So we have this, this here is 30. This is now 70 meters per second. And we have dy and the hypotenuse that we don't know. We don't actually know the total velocity, but we could find it if we wanted to. Total initial velocity. And I said the wrong thing. This should be VIY that we would be looking for. This is VIX, all right? So to find the velocity in the y direction, the initial velocity, we need something that is the opposite over the adjacent, because we have VIY over VIX, which is VIY over 70 meters per second. And that is the same thing as opposite over adjacent, which is tangent. So it would be the tan of 30 is equal to VIY time divided by 70. So we can say 70 meters per second times tan 30 is equal to VIY. And that is going to be equal to, and that's equal to 40.4 meters per second. Okay. So then we have a different problem. It says an outfielder throws a baseball to the first baseman at a speed of 19.6 meters per second. This is going back to the one we were working on previously, but this time we want to find out how long the ball was in the air. So we just redraw our diagram real quick. This is saying that they're the same height. Just excuse my poor drawing skills. We're saying that they're at the same height, okay? So this is going to be when we need to break things up into x and y components. So we already found the VI in the x direction, and we said that it is 16.97 meters per second, and the initial velocity in the y direction is 9.8 meters per second. And now this sounds a little bit tricky because we've been working with the d equals VIT plus 1/2 AT squared equation. But let's go through and write down our knowns and unknowns. We know the initial velocity. It's not 0 this time, so pay attention to that. The acceleration in the y direction is still a negative 9.8 meters per second squared. We don't know the distance. We just know that it's the same distance. And we don't know the time. That's what we're looking for. So, because this right here is the time. T is equal to, I don't know. So T equals, I don't know. So, if you remember from when we did free fall problems, we had a problem where we had somebody who had a ball and they threw it straight up and they threw it straight down, and then it came straight back down. And at this point right here, the velocity was 0 meters per second. Now, in this case right here, this one right here, there isn't a distance in the x direction because we're only dealing with the vertical component. But the distance in the y direction is like that. So we can take this and apply it to the y component here. So let's do that. If we do that, let's look at our motion equations in our reference table. And we can see that we have an equation that has initial velocity, and it has acceleration, and it has time, but we need a final velocity. And we know here that if we use symmetry, this right here has a final velocity of 0. Because it comes to a stop right there. It just means that we take only half of this problem and use symmetry to our advantage. So I'm going to erase this here just so that we can be working with only the one problem. But we can use this right here to our advantage. So we want to say that T up is what we're going to be looking for in the VF equals VI plus a T up equation. So we want this. So we can solve VF minus VI is equal to AT. All I did was I subtracted this term here, and it gets you this. So then you divide by the acceleration on both sides. So then T up is equal to VF minus VI divided by A. Alright? I'm going to go to a new page so that we have a little bit more room. So we ended up with VF minus VI divided by A is equal to T up. And our VF was 0. Our VI was 9.8 meters per second. And our A was 9.81 meters per second squared. Alright? So this will a negative 9.81 meters per second squared because it's gravity. So then we have negative 9.8 meters per second divided by a negative 9.81 meters per second squared. This gives us 0.998 seconds. And this is for T up. Now, it wants to know the total time. So if this is just T up, we then need T down. So T down is the same as T up. So T up equals 1 second. T down equals 1 second. And then the total time, we just add them together. And that's equal to 2 seconds. Alright? Okay, the last one is a golf ball leaves a golf club with an initial velocity of 40 meters per second at an angle of 40 degrees to the horizontal. What is the total horizontal distance traveled by the golf ball? This is another you try, so go ahead and you do it. So just like before, we have an initial velocity of 40 meters per second. So we need to break it up into x and y components. So the Vix is equal to that, and the Viy is equal to that. So the Viy is equal to 40 sine 40. This comes from Vi sine theta, Viy, that we said before. And that just gives us 25.7 meters per second. The Vix is going to be Vi cosine theta. So we can just go ahead and say 40 cosine 40. And that gives us 30.6 meters per second. Now, I'm going to go to a new page. Alright, so we ended up with initial velocities in the x and y component, x and y direction, so we can add those to an x and y motion chart. So let's go ahead and do that. So in the y direction, we had an initial velocity of 25.7 meters per second, and in the x direction, it was 30.6 meters per second. So from our problem, we can say that the acceleration is equal to a negative g, which is equal to a negative 9.81 meters per second squared. It wants the total horizontal distance, so this is equal to Vix. We need the horizontal distance, and in the horizontal, the only way to get that is to use the equation d over t, Vx equals d over t. However, we're missing both distance and time, but just like with the horizontal projectiles, the time on both sides is still the same. So we can find the time on the y side and apply it to the x. And just like we did in the last problem, we can use the equation Vf equals Vi plus At up, because again, this is going to get hit by the golf club, the ball, and then it's going to go up and it's going to come straight back down. So we're going to break it up into two parts, and we're going to solve for time right here. So Vf, actually, let me go back. We can subtract Vi to the other side. So then it's Vf minus Vi equals At up. Divide by A. And then we can find the time in the up direction. So we have Vf minus Vi divided by A equals T up. That's where we left off on the other page. Vf was 0 meters per second. Vi was 25.7, because we're working in the y direction, because we don't have an acceleration in the x direction, so we can't use it. Negative 9.81 meters per second squared for the acceleration. And this will then get us a time of 2.62 seconds up. This is t up. So then the total time is equal to 2 times t up. So it's equal to 2 times 2.62 seconds, and we get 5.24 seconds. and that is our time. Now, the actual question asked for the horizontal distance. So we wanted to know the total distance in the x direction. So we had a v initial in the x direction of 30.6 meters per second, and the distance was what we were looking for, and we have the time now. So then we can do v equals d over t times t and solve for d. So d equals v times t. Distance is equal to 30.6 meters per second times 5.24 seconds, and we get a distance of 160.34 meters. And this is the distance in the x direction. So the golf ball hits the ball and it goes into the air and lands. We're talking about this distance right here. That's what we're just found. Okay? All right. Hopefully this helps.